right, hello everybody. Today we are talking about reaction rates. So this is Unit 9, Lesson 4. Today we're going to describe the factors that affect the rate of a reaction and explain some of those factors using what's called collision theory. Okay, so before we jump in here, try to answer this do now question. How could you speed up or slow down a chemical reaction? Right, so think about, let's give an example, like Alka-Seltzer, when you put it in water, right, you've seen that it bubbles up, it causes a reaction. How could you speed up that reaction? See if you can come up with like 2 or 3 ways you could speed up that reaction. Go ahead and pause, come up with those 2 to 3 ways. Okay, hopefully you paused and came up with a couple. I'm going to go over the different ways in which we can change the rate of a reaction today. So when I do that, see if the things you came up with in the do now apply to the rate of a reaction. So before we jump into those factors that affect the rates of reactions, let's talk about this general idea of chemical kinetics, right? The unit is called kinetics and equilibrium. We haven't talked about equilibrium yet. That'll be tomorrow or the next lesson. But kinetics, right, you might notice kinetic energy, right, is the energy of motion. And chemical kinetics is really about the motion of the reactant particles in a chemical reaction and how that affects the way a reaction is going to occur. So chemical kinetics is the branch of chemistry that concerns itself with the speed of chemical reactions, known as reaction rates, as well as the way a reaction occurs, which is called the reaction mechanism. I'm going to talk a little bit about the reaction mechanisms right now, but we're going to focus mostly on the reaction rates. So in terms of mechanisms, right, most chemical reactions actually occur in a series of steps. They're sometimes called elementary steps or intermediate steps. And basically, why is that important? Well, not all the steps happen at the same rate. And so the slowest step is going to determine the rate of the overall reaction. And we call that the rate limiting step. And you can think of it as a bottleneck, right? A bottleneck is a situation where we have some factor that's slowing the rate of the entire, in this case, reaction. The simplest, right? Think of an actual bottle, right? If you pour water out of a glass, it all comes out very quickly. Well, when you have a bottleneck, right, it slows the rate at which the water can come out or whatever's in the bottle. And that's the idea of a bottleneck, right? It slows the speed at which, it kind of determines the rate at which something can happen by slowing it down. The slowest step in a reaction is going to determine the rate of the overall reaction. We have to talk about collision theory, right? Collision theory, it's really simple. It says that a reaction will occur when particles, and that could be atoms or molecules, collide with the proper energy and orientation. If they do, that's called an effective collision, right? I always picture like somebody throwing a bunch of Legos in the air, right? And if you want two Legos to stick together, not only do they have to run into each other with the right speed, right, or energy, but they also have to be positioned the right way so that they click together, right? And that's the orientation. And if that happens, you have an effective collision. The Legos will stick together. It'll form a new product, right? That combination is a new substance in this example. So remember, it's proper energy and orientation, and that makes an effective collision. So how can we affect the reaction rate, right? What factors can change the rate at which a reaction occurs? So this is right from the do now. See if you got any of these at the top of the lesson. The first one you probably didn't get. And this has to do with the nature of the reactants, so what the reactants are. In a solution, right, ionic compounds, this is just one example, right? Ionic compounds tend to react more quickly than covalent compounds because in ionic compounds, there's usually fewer bonds that need to be broken and then formed. Whereas covalent compounds, right, they can have many, many bonds that need to be broken and formed, but also they can have double and triple bonds, which take more energy to break. So ionic compounds tend to react more quickly. So it matters what the reactant is, right? If you're comparing two different substances, then you can say the difference in the rate of reaction some of that has to be due to the nature of the reactants themselves. It also matters the concentration of the reactants, right? So if we increase the concentration, what we're doing is we're increasing the number of the reactant particles in the same area. And if we do that, they're going to run into each other more often, right? So that's going to increase the number of effective collisions. They're going to run into each other more often with the proper energy and orientation, and thus the reaction rate is going to increase. So increasing the concentration of the reactants will increase the rate of the reaction as well. Here's the one most people get, so maybe you got this one. Temperature is going to affect the reaction rate. So remember that temperature is just a measurement of the average kinetic energy of the particles in a substance. So if we increase the temperature, we're increasing the speed at which those particles are moving, right? Which means they're going to run into each other more often, which increases the number of effective collisions, thus increasing the reaction rate. So if you increase the temperature, you increase the rate of the reaction because you're causing the particles to run into each other more often. Right? It's all about getting the particles to run into each other more often if you're trying to increase the reaction rate. And you can do that by increasing the concentration, increasing the temperature, and increasing the surface area. This one's a little tricky. So if you think about the Alka-Seltzer example, right? If you drop a whole tablet of Alka-Seltzer into water, it'll react fairly quickly. But if you crush up that tablet, thus increasing the surface area, the particles are going to run in. Now you have, right, you've created more particles, right, that are able to, well, you haven't created more particles, but you've broken them up enough so that the surface area increases so that they can now run into each other more often, right? More surface area means more area to run into for the particles to run into each other. So increasing the surface area increases the number of effective collisions and increases the reaction rate. Finally, catalysts. Right? We talked about this a couple lessons ago. Catalysts are going to increase the rate of a reaction by lowering the activation energy. If you remember back to our lesson on potential energy diagrams, lesson 2, that's when we lowered the energy hill. Right? Catalyst increases the rate of a reaction by lowering the energy hill, by lowering the activation energy. Okay, so a lot of information on this slide. Feel free to pause here, take a couple notes, replay it. But this is basically this is the information for today. And from here, we're just going to do a couple of example questions. All right, so go ahead, feel free to pause and rewind. I'm going to move on. So what might be a couple questions you might see about this stuff? All right, let's do this one. A 1 cubic centimeter cube of sodium reacts more quickly in water at 25 degrees Celsius than does a 1 cubic centimeter cube of calcium at 25 degrees Celsius. So I'm going to pause right there. So first of all, I'm noticing temperature is the same. 1 cubic centimeter, that's going to be the surface area, right? So that's exactly the same. And I'm already noticing, look, we have two different substances. If we're talking about the reaction rate of two different substances, then what those substances are matters. So if I look at my answer choices, I said the surface areas are the same. The natures of the metals, okay, they're different metals, so the natures are different, thus that's going to affect the reaction rate. So the answer is going to be B. Excuse me. Well, let's look at the other answers too. Density was not one of the factors, so that's not it. Concentration was, but right, what we should focus on here, we don't really know the concentration, right? We don't know how much water we have, so we can't really pick that one. But we know the two metals are different, so this has to be dependent on the natures of the metals, because if they were the same exact metal, then we couldn't pick B, because the nature would be the same. But since it's two different metals, two different natures, right, different properties, they have different reactivities, so the answer is B. That's what's determining the different rates of reaction. Okay, number 2. Raising the temperature speeds up the rate of a chemical reaction. We know that, right? By increasing, all right, let's see here, the effectiveness of the collisions. That's true, but maybe not only. The frequency of the collisions, that's also true. So, yep, our answer is going to be C, both the effectiveness and the frequency of the collisions. Okay? So if we're speeding up a chemical reaction, the answer is always C, right? We're increasing the effectiveness, we're increasing the frequency of the collisions always if we're increasing the rate. That's what collision theory says, right? So 2 is C, right? And 2 will always be C. Even if it was raising the concentration speeds up the rate of a chemical reaction by, well, same thing. Both the effectiveness and the frequency of the collisions are increased as well. All right, so 1 is B, 2 is C, okay? Now it's your turn, right? Now you should definitely pause. You can always pause on these ones, the examples too, before I even do one, right? Feel free to pause before I go over those, see if you can answer them yourself. But these ones I really do want you to pause and try to answer 1, 2, 3 before you move on in the video. Okay, so hopefully you did that, right? Because if you try to answer these before I go over them, the information is just going to stick better, even if you get it wrong. Trying to answer these questions is just going to help you. Okay, so what are the factors that affect the rate of reaction, and how do they affect the rate of reaction? Okay, I know there were 5, so let's see if I can get these. It's the nature of the reactants, right? And one example would be ionic compounds react faster than covalent. That's just one example. We had concentration. Greater the concentration, the greater the speed of reaction. Temperature. You increase the temperature, you increase the reaction rate. What was the other one? I know catalyst, right? The addition of a catalyst increases the reaction rate. Oh, and surface area. If you increase the surface area of the reactants, you increase the reaction rate. All right. So that was basically that one slide a couple of slides ago. Definitely go back and review that if you need to. Describe collision theory in your own words. So for me, I gave you the Lego example. That's how I think about it. So collision theory is really about two particles will react if they run into each other at the proper speed and in the proper orientation is the best word. Trying to use a different word. Alignment. If they align perfectly and they hit each other at the right speed, then they're going to react. That's basically what collision theory says. Okay, number 3. Given the reaction A plus B turns into C and D, the reaction will most likely occur at the greatest rate if A and B represent nonpolar. Okay, so definitely not the solid phase one, right? Solutions are going to react faster than solid phase. Just think about how free the particles are, right? In a solid, they're all locked into place. So I'm going to get rid of A and B. I know that solutions are liquids with things dissolved in them, right? We have a solvent, solute. There's more motion there. There's more free-flowing particles. And then if you remember, right, we said that ionic compounds react faster in solutions, right? So the answer here is going to be D, solutions of ionic compounds. All right, that one's pretty specific. I haven't seen a Regents question exactly like that. So, apparently Regents doesn't happen anymore, but, that's beside the facts here. So the answer for that is D. And that's as hard as it gets. So I recommend jumping right to the homework now. I think there's like 8 multiple choice questions. They're all pretty similar to these. I'm going to end it right there. A nice short lesson. All right, I will see you guys in a couple days for the next lesson or on Google Meet. Not Zoom anymore, Google Meet. All right, see you guys later.